In the following video lecture, we're going to discuss the Sn1 reaction mechanism. This is called the nucleophilic substitution reaction mechanism, and this reaction mechanism applies to tertiary halogenoalkanes. Tertiary halogenoalkanes, that's the first thing that we are going to define. Tertiary halogenoalkanes are halogenoalkanes where carbon that is bonded to chlorine. Now this carbon that is bonded to chlorine would on three sides be bonded to, it would not be bonded to hydrogens, but instead it would be bonded to some carbon chain. So there would be a carbon chain. For example, there would be CH3 on one side, carbon chain CH2, CH3 on another side, and there could be another CH3 on the third side. So a tertiary halogenoalkane is you're going to look at the carbon atom that is bonded to this halogen over here. It could be chlorine, bromine, or iodine, and focus on that carbon atom and see whether it's bonded to three separate carbon chains, or vice versa. You can see if it's not bonded to hydrogen. So this halogenoalkane would be called a tertiary halogenoalkane. So I've drawn another example over here of a tertiary halogenoalkane. So how to identify a tertiary halogenoalkane? There's a halogen attached to a carbon atom. So only focus on this carbon atom. So this is where you should focus. This would help you identify. Focus on this carbon atom. And on one side there's a carbon chain. On the other side there's a carbon chain as well. On the third side there's a carbon chain. So on all three sides there are carbon chains attached. So this would be called a tertiary halogenoalkane as well. Here's a third example, and this time I've drawn a skeletal formula. Things would be slightly trickier when you're dealing with skeletal formulas instead of these displayed or structural formulas. If you look at the skeletal formula, then you're going to focus on this node over here. This is where the carbon atom is, that is bonded to Cl. So if you focus on this carbon atom, you will notice that on all three sides, it's basically connected. It's connected to a carbon chain. There are no hydrogens attached. So this carbon atom and this halogenoalkane would be considered a tertiary halogenoalkane. This carbon atom is connected to carbon atoms or carbon chains on all sides. And this fourth example that I've drawn is basically it's not a tertiary halogenoalkane. So I've this example just to identify what is not a tertiary halogenoalkane. So again, I'm going to focus on this carbon atom over here. This carbon atom that is connected to this bromine, this halogen. If you look at this carbon atom, then this carbon atom is connected to a carbon chain on one side. It's connected to a carbon chain on the other side. But there's no third carbon chain, which means there's on the third side there's going to be a hydrogen atom. So this carbon atom, or this alpha carbon atom, which is sometimes referred to as the alpha carbon atom, on which the halogen is attached. So this carbon atom is not connected to three carbon chains, which means that this one is not going to be tertiary. So it's not a tertiary halogenoalkane. So the reaction mechanism that we are going to discuss now only applies to tertiary halogenoalkanes. It doesn't apply to primary halogenoalkanes, which we discussed in a previous reaction. The mechanism for that would be Sn2. This Sn1 only deals with tertiary halogenoalkanes. We are now going to discuss the reaction mechanism, which is Sn1 for tertiary halogenoalkanes. So I've drawn a halogenoalkane, and it's a tertiary halogenoalkane. If you look at this carbon atom, which is bonded to chlorine, you would notice that this carbon atom over here is bonded to three separate carbon chains. There's a carbon on over here as well, one on this side, one on top. So there are three different carbon chains coming out of that carbon atom. So this is classified as a tertiary halogenoalkane. And we are talking about nucleophilic substitution reaction. So exactly like the previous case, we have three nucleophiles. You can have the OH minus one nucleophile. The negative charge would be attracted to positive charges, and you have the ammonia nucleophile, which has lone pairs, and you have the cyanide nucleophile. The conditions for the reactions are also given, which we have previously discussed as well. The OH nucleophile, you add NaOH, and then you reflux this halogenoalkane with it For ammonia, you use ethanolic ammonia, and then you use reflux, and for NaCN, you use ethanolic NaCN, and you reflux. So these are the conditions. So I'm going to pick the OH nucleophile first, and the first thing that I'm going to discuss is, like the previous Sn2 mechanism as well, this CCl bond is very polarized. There are two electrons being shared by carbon and chlorine, but chlorine, being the more electronegative element, is capable of pulling this electron closer to it. So chlorine is more electronegative, and so the shared pair of electrons are unequally shared. They're lying closer to chlorine. So if they're closer to chlorine, chlorine would have a slight negative charge, whereas this carbon atom over here is going to have a slight positive charge. So this is a polarized bond. All the other bonds are almost non-polar. So this bond is highly polarized. And this positive carbon atom it should attract these negative nucleophiles. So the electrons from these nucleophiles, let's pick the OH nucleophile. So the electrons from the OH nucleophile would be attracted to that positive carbon atom, but there's a problem. Unlike the Sn2 mechanism, this OH nucleophile would not be able to get close to this carbon atom. If you look at the surrounding of this carbon atom, you would notice that there are carbon chains on all sides, and those carbon chains further have hydrogens around them. So this OH-1 has no path. It cannot approach this carbon atom. So this OH-1 in the first step would not actually be able to even get sufficiently close to this carbon atom. So this carbon positive, which has a slight positive charge, would in fact actually not be able to attract this OH-1 nucleophile, for the reason that it's completely surrounded. There is no path. All routes reaching that carbon atom, because it's right in the middle of the molecule, all routes are blocked. So this nucleophile would actually not even get close to this carbon atom. So this arrow should be there in the first step, because the OH-1 nucleophile would not be able to approach that carbon atom. So what happens? What happens is that during collisions, there's a very slight possibility that this bond, which is already polarized, it would break. And these electrons would be pulled by the chlorine, and the Cl-1 ion would be formed. So a very slight possibility exists. So when you heat this halogenalkane, there would be excessive collisions, and during collisions, there's a lot of chance that this Cl atom, along with its electrons, would break off and form a carbocation and a Cl-1 ion. So as you can see now, this is my carbocation. The shared pair of electrons, the bond that was being formed between the carbon and the Cl, it broke off. Cl took away all the electrons and ended up forming Cl-1, because it's very electronegative, so it's going to attract those electrons strongly. And carbon lost its electrons, so this carbon has a positive charge. So this is my carbocation that is formed. And this would be referred to as an intermediate, because this is a very stable carbocation, and the reason why it's a very stable carbocation is that this positive carbon in the center is right in the center, and it's surrounded by large atoms. On all sides there are carbon chains, and carbon chains have a lot of electrons. And another thing about carbon chains is that they have an electron donating effect. Whenever there's a carbon chain attached to anything, that carbon chain is going to push electrons towards that group. Similarly, this carbon would also push electrons towards this carbon over here, because this carbon is electron deficient. It's positive. So vice versa, it would be attracting electrons from all the other carbon atoms. And when those electrons get attracted to by this carbon atom, the positive charge density would decrease. So I've written that down as well. So the electron donating effect of the carbon chain. So all these carbon chains are pushing electrons towards this positive carbon in the center. Vice versa, the positive carbon is attracting their electrons. And so this positive charge density on the carbocation decreases, and this is what's making it more stable. So it's a very stable carbocation intermediate. And by the term intermediate, what I mean is that this now is a two-step reaction. So this is This is step 1 of the reaction, and this would be a slow step because to break the CCl bond, you would have to wait, you would have to give it energy. The polarizing of the CCl bond is going to take a lot of time, so it's going to be a relatively slow step. So this is my first step, and what happens in the next step is that the OH-1 nucleophile, remember this OH-1 nucleophile was not able to get close to this carbon atom, now has a path and it would be directly attracted to this positive carbon atom because now there's space. The atom that was attached over here is now gone. This Cl-1 has broken off. So now there's room where this OH-1 could fit in. So its electrons are going to be attracted by this positive carbon atom and it's going to form a bond. Plus it's going to be this second step is going to be a very fast step because this is a negative ion, whereas this carbon now is a positive ion. So the attraction would be very strong and very quickly this second step of the reaction would occur and the product would be formed. And this over here is the product that would be formed. The OH goes and bonds with the carbon, the positive carbon atom that we drew earlier. So this OH nucleophile, OH-1 nucleophile is going to be quickly attracted to this positive carbon atom and it's going to bond with that carbon atom. So this is the product that would be formed. The end result is that the Cl that was previously present on this carbon atom attached to this carbon atom is knocked out and the OH nucleophile has substituted it. Hence the term substitution reaction. Plus I'm also going to write down that this is now a very, very fast step. And we are also now going to discuss why this reaction is called Sn1 mechanism. Why is there a 1 written over here in its name? Now remember that this is a two-step reaction. There's a slow step, an intermediate carbocation intermediate is formed, and then there's a fast step. Now if you look at this reaction, the OH nucleophile, my other reactant, I had two reactants. One was the halogenalkane and the other one was the nucleophile OH, and let's pick OH, and I picked the OH-1 nucleophile. Now this OH-1 nucleophile only has something to do in the second step, which is the fast step. Now let's assume that this slow step is taking 100 seconds, whereas this fast step is taking 1 second, and the overall reaction is taking us 101 seconds in total. Now if I increase the concentration of OH-1, then the rate of the slow step would not increase, but the rate of the fast step would increase. So if it increases, and if it was previously taking 1 second and now it's taking 0.5 seconds, and I doubled the concentration of OH-1, there would be hardly any effect on the overall rate of the reaction because previously it was taking 100 seconds plus 1 second over here, so it was taking 101 seconds. Now I've increased this rate. Now this slow step is taking still 100 seconds, whereas this is taking 0.5 seconds. So the rate of reaction increased from 101 seconds to 100.5 seconds. No matter how much I increase the concentration of OH-1, let's take it to infinity, and let's assume that this reaction almost takes 0 seconds now. The overall rate of the reaction or speed of the reaction is still taking 100 seconds, so there would hardly be any effect on the overall rate of the reaction. So what that means is that the rate of the reaction is not dependent on the concentration of OH-1 ion. No matter how much you increase the concentration of OH-1, the rate of the reaction would hardly be changed at all. But if you increase the rate of reaction of the slow step, let's say this is taking 100 seconds and I double the concentration of the halogenalkane, then the collisions would double. There would be more chances of Cl-1 breaking off, so the rate of the reaction might drop from 100 seconds to 50 seconds. So if the slow step increases, the overall rate of the reaction would increase. So rate only depends on the slow step. Hence, it would only depend on the concentration of this halogenalkane. So it would only be dependent on one of your reactants, not both of your reactants. Hence, this term 1. So this 1 means that your rate is only dependent on only one of the reactants, not the other one. So not on the nucleophile. And one more thing that needs to be remembered about this reaction mechanism is that it's a two-step reaction mechanism. The first one being the slow step, having the high activation energy, and it results in the formation of this carbocation with the nucleophile, and the next step the nucleophile attaches with this carbocation forming the product. So it's a two-step reaction mechanism that needs to be clearly understood. Unlike the previous Sn2 reaction mechanism, that was a one-step reaction mechanism. We also discussed this nucleophilic substitution reaction Sn1 mechanism with OH minus 1 nucleophiles. If you used the other ammonia or cyanide ions nucleophile, the reaction mechanism would be exactly the same. The first step would be exactly the same. There would be no difference. In the second step, instead of having these OH ions, you can substitute these OH ions with if you have the cyanide cyanide nucleophile, you're going to replace it with the Cn minus 1 nucleophile, and your product, instead of having an OH getting attached over here, there would be a Cn nucleophile that would be attached over here. So that would be the reaction mechanism with Cn minus 1. Vice versa, if I want to see the reaction mechanism with ammonia, then simply replace this Cn minus 1 nucleophile with the NH3 nucleophile. So lone pairs on N are going to get attracted to this carbocation and they're going to bond with it. So in your product, instead of having this Cn ion, you can have ammonia getting attached over here. Remember that this ammonia, because it's a neutral molecule, and an ammonium ion instead would be this N over here is going to have a positive charge instead. And like the previous mechanism, there's going to be a reversible reaction. This H might lose its electron, it might end up forming HCl. So there's going to be a reversible reaction, which would be something like this. That this H over here loses its electrons because N is making too many bonds, and it would end up forming HCl. It would go and bond, it would bond with the electrons from Cl, and they would form HCl, whereas the rest of the molecule would be, it would be this thing over here with N getting the electrons from and reforming its lone pairs, and HCl would be formed, and this would be considered a reversible reaction. So there's going to be a reversible reaction between these between the products. So an alkyl amine would be formed, or an alkyl ammonium ion would be formed. These two products would be present simultaneously in your products.